First, I would like to welcome everyone to 477 class. This is a class called Introduction to Algorithms. Although the name is Introduction, it's kind of a seriously introduction to algorithm. You learn a lot of real stuff. It's not that gentle. You learn a lot of cool algorithm in this class. Okay. My name is Tachapon Saranurak. This is how it's pronounced, but whatever you pronounce, I don't mind. Yep. And in this class, we have one GSI, which is Benyu Wang. Can you show yourself? Okay. So he's my own PhD student, and he will be GSI for this class. And yeah, for this first class, it's going to be quite easygoing. I will just start by kind of try to motivate why we want to study this, the stuff in this class. And by the end of the class, we go through some logistics information. Okay. So yeah, for today, I want just to kind of motivate why do we study algorithm or TCS, theoretical computer science at all. Okay. So I will start with mention some ideas from TCS that changed the world, and then next I will mention some of my own story, some of my research that how it's like to be algorithm designer, and then we will talk about what you will learn from this class, how to learn from this class, how to effectively learn things from here. Okay, and by the end we look into logistics information. Okay, let's start with this. I'm gonna talk about 3 big examples, which is very basic question: multiplication, factorization, and shortest path. Okay. So the first question we look at, the first problem we look at today is multiplication. The problem is very simple, computational problem. You have 2 numbers, A and B, right? And let's say they both have n digits. You just want to multiply them. Okay? And everyone learned how to do this in grade school. In grade school, we learn how to do this using some algorithm that takes n squared time. And the algorithm looks like this, like a tabular multiplication. You multiply 1 to this first number, and then you get this one. Multiply 2 to this whole first number, shift it by 1, and here. Just do this. Everyone learned how to do this. But you see that when these 2 numbers have 5 digits, you kind of need something like 5 square operation, right? Just to write this thing down, you kind of need 5 square operation already. And in general, you take n square operation. So it's an algorithm that works correctly. We love it. And it's known for a long time, more than 4,000 years actually, invented by Babylonian people. But the thing that we always ask ourselves, right? Whenever we have some problem, we can always ask, can we do better? And this is kind of the research question that we can just ask to any question, any computational problem that we encounter. And there is a interesting history to this research question. So something like 60 years ago, there is an influential mathematician from Russia called Kolmogorov. He's the one who invented Kolmogorov complexity and many other interesting concepts. So he worked on this, and he want to conjecture that, okay, no one can improve this. You kind of need n square operation up to constant factor. Okay, so he tried to announce a seminar that he gonna try to show this, why you need n square operation to multiply 2 numbers. It turns out that within a week, one of his students called Karasuba just discovered a way to multiply 2 numbers in a faster running time, which is n to the 1.58. And it turns out that, okay, the algorithm is quite simple, and we will learn this algorithm as the first algorithm from this class. By the way, I want to ask, like, how many of you have seen this algorithm already? Okay, cool. So you learned it from 376, right? Okay, good. I'm gonna still talk about it so that I can introduce to like a cooler ideas. Okay? But you see, this is like the first improvement in like super long time, which is impressive. Okay, you see this improvement, you can ask again, can you do better? And people try, and there are like a lot of improvement. And there is a significant improvement in the 70, where like they can do it in n log n log n, which is much, much faster. And there are more improvement. And just quite not too long ago, like 5 years ago, now people can get it down to n log n, which is looks nice, looks like a nice bound. And interestingly, okay, can we do better? Interestingly, there is also a recent lower bound, like not really lower bound, but conditional lower bound, saying that actually you would need n log n time, assuming some conjecture called network coding conjecture. And this is actually a surprising connection because this conjecture kind of have nothing to do, superficially, it has nothing to do with multiplication. It's actually about like a conjecture that is about how to send information through networks, which is like, it seems like no one would thought that it has connection to this. And this kind of surprising connection appears again and again in TCS. And you see some interesting connection in this class too. But I will not talk about this. You can look at this paper if you want to read it. It's actually a simple argument. Just search this name and this keyword. You will find it. Okay. But anyway, this new improvement, that is the impressive improvement here, that is much, much better than n squared. They are based on something called fast Fourier transform. And this is a concept that we will learn in this class too. Just right after I talk about Karasuba algorithm, you learn about fast Fourier transform. Okay. And this algorithm is one of the very influential algorithm. It's so impactful. It's used in like image processing, and also like it's one of the key like kind of the generalization of fast Fourier transform. It's used a lot in quantum algorithms. Okay. So this is kind of invented long ago, like 60 years ago, and one can argue that it has been kind of discovered before, like by hundreds of years by Gauss. You see what it is next class. Okay. But I want to just point out that, okay, there are so many basic tasks in everyday life, and like improvement actually is always possible. And you see that even recent improvement is possible, like just 5 years ago, even for tasks like multiplication. And I hope to maybe like throughout the class, I will try to point out the open problem that that you can hope to improve, okay, in this class. But anyway, even now, you can still ask, can you improve multiplication beyond n log n? If you don't believe in that conjecture, network coding conjecture. Or can we try to prove lower bound? But like another way to put this question is that, is it the case that multiplication is inherently harder than addition? Because if you have two n-digit numbers and you want to add them, the grade school algorithm that you learn would take something like order of n time, right? Just look at each digit and kind of add them one by one with some carries. So that takes n order of n. is it true that addition is strictly easier than multiplication, or they kind of are the same up to constant factor? No one knows until now. So this is like an interesting question. Okay, next problem, factorization. So this problem is kind of the inverse question of multiplication, right? You have a number C, and you just want to output two numbers A and B that multiply to C. A simple question that we can ask, and is actually important in cryptography. Now the trivial algorithm, you can do it. For example, if you are given C, you can try a for loop from A, from A equals 2 equals 3 up to root C, and just check if A divides C. If one of the iteration here, A divides C, then you know that okay, you can factor C. But if none of this, if none of this A divides C, then you can claim that C is a prime number, so you cannot factor, right? So this is a simple algorithm that works. But if you observe how fast this algorithm is, you can see that it's exponentially slow, right? Because if C have n digits, then C can be as big. C can be as big as 10 to the n, and so square root C can be as big as 10 to the n over 2. Okay, so so this algorithm can take like 10 to the n over 2 operations. That is exponentially slow, so not great, right? And so can we ask, can we do better, right? And it turns out that okay, people have tried really a lot, and there are some algorithms that is faster. So where the running time, so you can write this algorithm as something like some constant to the order of n, right? But there are algorithms that the thing in the exponent is not order of n, but it's order of n to the 1/3. So that is like a impressive improvement. But still, this kind of running time is not a polynomial running time. It's not really efficient yet. And no one knows until now how to do it faster. So should we be sad about this? It turns out that not always. This is because difficult problems can also be useful. Like this is a lesson from cryptography, the big lesson that we learned from TCS. That is, when people have tried a lot and failed for some computational problem, no one can find fast algorithm. You can flip this and use it and exploit this hardness. Okay, so what happened is that Rivest, Chamier, and Edelman, like 50 years ago now, actually, show something like this. That is, if factorization is hard, then you can use it to get like a security of internet. If you took 376, you learn that like RSA gives you public key cryptography system, and that is basically the reason why you can do e-commerce security, right? So that's a great thing. So that's the theme of modern cryptography, and basically whenever some problem is hard to compute, it usually implies some magic that you can exploit. And I will not go into this that much, but if you want to know what kind of magic you can do, you can look up and search for what is zero knowledge proof, or what is fully homomorphic encryption. It's like some, at the first time that you hear it and learn the definition, it seems impossible that you can do, but it turns out that you can, assuming that some problem is hard. Okay. So this is another take-home message from TCS that difficult problems actually are useful. Okay. So at least it gives us internet security and more. There is one plot twist actually that in the 90s, Peter Shaw actually shows that if you can actually invent quantum computers, then you can factor in n squared time. This is polynomial time now. And so it means that if you can really invent quantum computer, then you can actually break internet security. So, but right now no one can invent quantum computer yet. We don't know when it will be real, but it makes the story quite interesting. What will be the future of internet? By the way, so this actually motivates the new era of cryptography, which is how to get security against quantum computer. And if you want to learn more about this, we have a local expert in our department, Chris Pikert. He is an expert on something called lattice-based cryptography, and you can look him up or talk to him.
Well, it won't me up the tiniest bit.
So that's the two interesting problem, and we learn a bunch about this. That and the next one is shortest path problem. Okay. So this is another super basic question where you have a graph, and you have, let's say the graph have n vertices and m edges, right? And there are two vertices, s and t. So you have a graph, you have s, you have t, and you have some graph like this. Okay. And maybe the graph has weights. Each edge has weights, and so on. And basically you want to ask, what is the shortest path from S to T? Okay, so long time ago, there is an algorithm called Bellman-Ford. We learned about this too. That takes mn time. It uses some kind of dynamic programming that we'll learn in this class. But now, Dijkstra show how to improve mn algorithm to m plus n log n. So this is a kind of quadratic improvement from something quadratic to linear, to almost linear. So this simple, this improvement from quadratic time to linear time actually is super influential. It is the one that enable the whole industry on internet, how to route information in the internet, or the algorithm in Google Maps and so on. And there is an interesting history about this that he actually invented this algorithm in just 20 minutes. So he just went shopping with his girlfriend, and he's tired and just want to sit down in some cafe without any pens and pencil. He said to himself he wanted to solve this problem, and he designed this algorithm very quickly without pen and papers. And because of this, because he need to keep everything in his head, the algorithm turns out to be super simple. And so sometimes you can do this. Not often you can do this. I almost never do this, for example. But yeah, this is an interesting thing that just one single algorithm can actually enable the whole industry. And you can ask, can we do something better to this algorithm that is almost linear? Okay, so this is already really good. What can you do further? Okay. It turns out that you can still do, right? There are still exciting development on shortest path, even until like last 2 years or last year. Okay. So one aspect you can ask is this. What if you want to solve this shortest path problem using parallel computation? Okay. For example, the goal might be that when you have many computers, you kind of want to spend the total work to be linear, but the parallel time should be like small, right? Like you might spend total work linear, but the parallel time might be like polylog time now. Yeah, because you have many computers, you can do everything in parallel. So this is a hope that you want, that people want to do. That's the question. You want to do something like linear work and polylog depth. By polylog depth, I mean the parallel time. Okay. And okay, so it turns out that this is not an easy question. And if you look into Dijkstra algorithm actually is inherently very sequential. Its algorithm actually has very large depth. It's not good for parallel computation at all. You can like kind of, if you know Dijkstra, we will cover Dijkstra in our class too. But the way it works is something like this animation, and it's super sequential. Okay. Now, just like the last 2 years, it turns out that people can compute shortest path in nonlinear work, but now the depth is just square root n. Okay, and no one knows if you can do it even further, and it's still an interesting open problem about super basic graph question until now. Okay. This is some problem that I try to work on as well, and we'll see what will happen. Okay. So what I want to point out about this part is that, okay, there are many well-known inventors that we learn from history that really changed the world, right? Edison that invent light bulbs, Gutenberg that invent printing press, and so on. Okay, they really are a real inventor. They changed the whole industry. But this is the same actually for algorithm designers. If you look into what Dijkstra did, he invented shortest path algorithm that is fast enough to be practical, and that allows internet routing, and like a fast Fourier transform that is invented by Cooley and Tucker. This is so influential, not just in TCS, but in like audio and image processing, and RSA, and so on. Okay, so these people that invent one piece of code or piece of ideas, this algorithm really changed the world. So they are like a heroes as well. Like the world has changed so much by just like in just a few decades. So I want to point out like how influential algorithm can be. Okay. So that's the take-home message that I want to convey to you. And actually, how algorithm affect our life is only accelerate in the age of AI and machine learning. You see that like they are more and more like affect us, and TCS and algorithm design is actually growing even faster nowadays. So like every year you see like an exciting algorithm invented, so it's an exciting area, and I hope you enjoy the things from this class too. Okay. So now let me tell you a bit about some of the algorithm that I look into as well, okay, and how I go into this area, how I went into this area. So this is going to be a story about the problem called dynamic spanning forest. Okay. Dynamic. Okay. By the way, if at any point you have question, something doesn't make sense, just ask, right? Like I'm super happy to get a question. Okay. All right. So what is dynamic spanning forest? I want to just tell you in high level about this. Okay. So in like the model of computation that you have learned from maybe other class or previous class is that you usually want to solve a problem from scratch and be done forever. That is, the model is like you have an input and the input is given to your computer. You read this input and then output the answer, and that's it, and finish, right? So this is like a static model of computation, but it doesn't really capture real world problems anymore. And the reason is that in real world, everything change, right? It keeps changing. When you have input as a graph, like internet graph, that graph keeps changing. The social network graph keep changing. The traffic, the road network, like the traffic in the road network keep changing. Everything that you really care a lot about is an input that is so big and it keeps changing. Okay. So the common theme in computation that people like want to solve actually looks like this. You want to solve like a same problem repeatedly because you care a lot about it. You want to compute about it so many times. But this input is so big and it keeps changing, right? So what we want, that like the model of computation that we kind of prefer is that, okay, the user have some input and he just feed how the input changed, like one bit of the input, how it changed to the computer. And the computer can just output the new out, like return the new output fast without like reading everything from scratch, right? If the input just changed by one bit, why should you do everything from scratch? So the goal is to get a fast update time. That is the time to return new output after each update. So this is what dynamic algorithm is about, right? This is the area called dynamic algorithms. How do you design, how to solve some problem and not recomputing everything from scratch when the input changed just by a bit. Okay. And this is a natural question, and people like it kind of invite many researchers to think about this. Many papers are published in these areas, and there are many algorithms, and I will just talk about this problem called dynamic spanning forest. So let me tell you what is spanning forest. Let me recall what it is. When you have a graph, this is a graph with vertices and edges, right? So spanning tree is like a subgraph, the red subgraph in this graph. Basically, it's a tree such that it includes all vertices in the graph. Okay. So it's a tree that is a graph with no cycle, and it's spanning, so it includes every node in the graph. And spanning forest is just a set of spanning tree on each connected component. Like like this picture. Okay. Makes sense, right? Okay. So dynamic spanning forest is the problem that looks like this. It's like you have a graph, and then there is an update to the graph. Let's say you want to delete one edge, like 1, 3. You want to delete this one, so you delete it. But then the red graph here is not spanning tree anymore, so you need to update it. So for example, you add this edge. Now you get a new spanning tree. So what you output is just you output how you change this spanning, this out, like how you change the red graph to get a new spanning forest. And once you are done with an edge update, then the new update will come. For example, here you insert one edge from 2 to 3. Now the red graph remains spanning forest, so you don't need to do anything. And then the next update can come to you. You want to delete 2 to 4, so delete this one. So now you need to update your red graph. Okay. And you output how you update it, and so on. So this is a problem. Does it make sense? Okay. So one trivial algorithm to do this is just to recompute everything from scratch after each update. How fast is this? Can you tell me?
Yeah, it's on this one, but it's not.
Yeah, no.
What's do you know the algorithm? How can we compute a spanning forest in a graph? What's the running time of that? Yep.
Is it E log E?
E log E, that would work too. Yeah. There is actually a fast algorithm. Like if you want to do E log E, maybe you want to do minimum spanning forest. But if you just want to do some spanning forest, can anyone tell me what kind of algorithm can you solve that? Can you do to solve it? Yep.
I think you just need to traverse through all the edges. Like for every edge, you note 2 vertices as visited, and then if both of them are visited, then you disregard that edge. You move to the next edge.
Yeah.
So you just iterate through all the edges.
Right.
Yeah.
Exactly. Good. So you might have learned about graph traversal, depth first search or breadth first search. Have you learned about this before? Okay. When you run depth first search or breadth first search algorithm, whenever you traverse to one vertex for the first time, then you just add that edge into your forest. And if you do this, you will produce a spanning forest to the graph. Okay. And the first search or breadth first search just take linear time, right? Like a V plus E or M plus N. Okay. So here you can do, you can get an algorithm that rebuild spanning forest from scratch. The update time is linear. Can we do faster? That's the question. Okay. So this is the question that we want. We want to maintain spanning forest in the graph, and each update is an insert or delete of an edge in the graph, and you want to output how we change the forest. Okay. So it turns out that, okay, people have thought about this, and 40 years ago, Frederickson showed that you can actually do better than linear. You can do it in square root m time. So that's already impressive. It's not that clear at all how to do this, and I will not tell you. But it can be done. And there are some improvement from root m to root n. And the story that one of my work is that like there are many improvements, but by the end, like 5 years ago, I could improve this to n to the little one. How you should think about n to the little one, like little of 1 is just something that kind of go to 0 when n grow to infinity, right? So it's something that is smaller than any polynomial, like n to the 1, n to the point 0.001, right? So you can think of n to the little 1 as something small. Okay. So this is like one of my work, and there are many things that happen here. For example, like there are like a lot of things here, and I want to tell you at least about the statement of what's going on here. What is randomized algorithm? What is amortized update time? We will learn about this concept in class too, in several, like maybe 4 lectures from now. Okay. But at least you learn about this term today. Okay. So, and this development kind of relate with my story as well. So, actually, back in my bachelor when I was in Thailand, like I kind of want to learn more about algorithms. I was participating in programming competition and I like it, so I want to learn more about it. Try to do research about this. There's like my mentor by that time. His name is Jittat. He just said okay, try to read this paper, the Holm et al. Paper, which is this one. Okay. And it turns out that okay, it takes me like a lot of months to just absorb like a little part of the paper. So in this, like if you read a paper for the first time, it can be really tough. But actually one of the project in this class is that I might not ask you to read the paper, but I will ask you to maybe read something that is not presented in class, but maybe from some other lecture notes, and you try to learn it yourself and then try to present to us. Okay? So at least it will train you how to learn things on your own and how to communicate that. But so the story is like, okay, I try to learn about this and kind of understood it, like not so deeply, but at least it got me interested in TCS. And I try to apply to, like when I finished my studies, my bachelor study, I try to apply to all the grad school in TCS. And it turns out that I got rejected from every place basically in the US. Luckily, there is some place in Germany that they don't need too much research experience, and I went there. Yeah. So that's what happened. But what is in this paper, this Holm et al. Paper? What they show is that they can show how to get update time that is polylog n. So way better than root n, right? Polylog is just much better than square root. But what they show is something that I say is amortized update time. So I want to tell you what it is. Okay. So what is amortized update time? It means this. It means like, in some sense, it means average update time. But it's average in this sense. It's in the sense that suppose that there are k updates to the graph, like 1 insertion, 2 insertion, like the sequence of updates. Let's say there are k of them. Then the total update time that this algorithm will spend is going to be something like k polylog n. So on average, it's something like polylog, but there can be some update that you spend so much time and then not so much time on average. Okay. So that's what it means to be amortized update time. Okay. In class, we will analyze this kind of data structure and you learn about this more. But the bad thing is that some update can be super slow, and but this cannot happen often. But we don't want this, right? What we want is we want to remove amortization. Every single update should be fast. That's what we want. And so this kind of lead me to the next chapter, which is I went to Germany at Saarland University, and then got exposed to many areas of TCS. And at first I was working on some area called complexity theory, okay? And actually started my PhD in that area. But then there was a talk by Varili King. She gave a talk, and her talk is actually about this problem, dynamic spanning forest. And what she shows is basically this one. This is by King. What she shows is that, she now can get polylog n update time as well. And it's not amortized anymore, so that's great. It's worst case on every update. However, her algorithm is randomized. That is, it can kind of it need to toss coin, and it's not always correct. Okay. So it's not amortized, but then it's randomized. Okay. So this is gonna be really this is super beautiful algorithm, by the way. I might this might be one of the projects that you can choose from to read about. Okay. It's really beautiful and just kind of inferential, but it can make error. It's not always correct. Okay. So not good. We don't want that. We want it to be always correct. Okay, but anyway, because of this talk, I kind of really want to work on this, and got interested in this problem again, and even decided to switch my PhD studies and work on this. So I switched and do a PhD in Sweden in KTH, and so basically keep working on this problem for 2 years. I get some partial result and keep getting rejection again. But my mentor by then, Danupon Anongkai, this guy, he kind of guide me what to think about when I got stuck. So advisor, if you want to do research, especially in theory, advisor really is important. They will guide you what you want to do when you got stuck. Okay. Anyway, we kind of got stuck for some time, try many approach, but then somehow I just randomly learned about this thing called expanded graph. There is some online seminar about this thing, so I try to learn about this, and then it turns out that it is a good tool. This random tool is a good tool for this problem. So what we managed to show is something. We show that together with my mentor, my advisor, we can improve n to the 1.5, n to the 0.5 square root n to something like n to the 0.494. So some improvement. It's randomized still, but at least now it's always correct. Okay. Meaning that if you know about this this kind of randomized algorithm is called Monte Carlo algorithm. This one is called Las Vegas algorithm. You don't need to remember these words, but just want to mention. Okay. But there's something, okay? But interestingly, at the same time, there is another guy by now friend, Christian Wolf Nielsen. He also show similar result. He can get something like running time, which is 10 to the point 4999, something like this. But for a harder problem of minimum spanning tree, minimum spanning forest, not just some spanning forest, but minimum. Okay. So that's great, and so we like, but it's a bit of a shame for me actually. Like I tried to work on this for like 2 years or something, and then another person can do it too. But anyway, we learn about each other and try to work on this together. And it turns out that like by just combining our ideas and introducing a new idea, we meet for 2 weeks and chat every day. And then like within 2 weeks, like we get basically all the high level idea, how to improve this kind of running time to just Enteleader 1. So that's a fun thing. And like then I spend basically half a year to just write it down. Like from getting high level idea correct to write it down formally, it can be long time, but that's how it works. Okay. So now it's almost, it seems very good now. Like the running time is fast, is 100% correct, but still it is randomized. So the last thing is to remove randomization. And so the rest of my PhD was just to try to remove randomization. But I try a lot and basically no success. Yeah.
Why is randomization bad?
Yeah. So good. So there are many answers to this, but for example, when you try to debug algorithm, or like when you try to write down any algorithm and want to debug it, if the algorithm is deterministic, then you know exactly in which, like, what is the configuration of your algorithm on every step. But on the other hand, if it's randomized, then the configuration can be depending on your coin tosses, and it makes make it more complicated. Yeah. So that's one thing. Another thing is it's more like also like a theory curiosity. You want it to remove all the things that you don't need. Yeah. Good question though. Yeah. Right. Okay. So yeah, like the rest of my PhD, I try to make it deterministic. No coin tossing. And but I didn't succeed. So that's when I went to do a postdoc at TTIC, Toyota Technological Institute at Chicago. And then like I learn and work with many great people. Like some of them is Julia Chusoy, Richard Peng, Jason Lee, Deb Maya, and so on. Yeah. And by talking with many people and try a lot, like eventually we can make it deterministic after almost 10 years of working on this problem. And the key technique is something called like expanded decomposition, deterministic expanded decomposition. But anyway, from this you make this, you get to this thing. So it's like a strict improvement from root n to Enteleader 1. So that looks like a good thing. However, this Enteleader 1, although it's much faster than root n, this Enteleader 1 actually is slower than Polylog by quite a lot. I didn't specify what is integer 1 here, but it looks like this. It looks like this thing actually looks like 2 to the square root log n. It might be hard for you to pass this, but it's something that is way bigger than Polylog, but way smaller than this one. Okay. So anyway, so the best goal would be actually make this thing improve this to Polylog. That would be the best, like the final ultimate goal. But until now, I cannot do it yet. Like I have tried to do this, but kind of give up. I don't know good techniques, so no success yet. But maybe like we can come up with a good technique in 5 years or something, or maybe by you. I don't know. Yeah. But anyway, like along the way, right? Like okay, I kind of got stuck in this, but I have been trying to explore the power of this thing, the expanders that I mentioned in Word, what it is. It's some powerful stuff. In Word, it's like a sparse graph that behave like a clique. So a clique is like a dense, like the densest graph, but here is like a sparse graph, and yet it behaves like a clique. I will not define it too much. You can look up the internet what it is, but it turns out to be super powerful stuff. Like I explore a lot about this, and there are many like a powerful application of this thing, and it leads to like a 20 papers, Foxstock paper, which is like a top conference paper in TCS. If you want to learn about this, I have actually taught a class about this. I have a tutorial and workshop about this. You can look into it. We recently kind of discovered a new type of expander called length constraint expander together with Bernard Heubler. But anyway, so the message I want to convey to you is that, okay, when, at least for me, when I do research, like it takes a lot of effort to do. There are like, can only make incremental improvement, but like this incremental improvement is something that, at least in our community, TCS community, we appreciate it. Each step we can publish in a good top conference, and it's like rewarding and fun. Like this class could be like the starting point of if you kind of want to do more and more on doing algorithm design. Okay, so now about this class. Okay, what and how to learn from this class. Okay. So what you will learn from this class, I hope that there will be like there are two goals from me. The first goal is that you learn new techniques or algorithmic paradigm from like inferential algorithms. So you learn both the algorithm itself that is inferential and useful, but not just that, you learn the techniques, you learn the paradigm, how to think in that way too. Okay. The hope is that once you know this, then in your career, when you encounter some problem, then you can like you have an intuition that, okay, maybe you can solve this kind of problem using this kind of algorithm. Okay, maybe it's a new kind of algorithm that you never seen before, but you learn from this class, and it kind of trigger in your mind that this is the way to do it. This is the way to solve this kind of thing easily. So there will be like many kind of paradigm that like many new ways of things that not in like for example 376 and you learn in this class. Another thing that you will do in this class is to train to rigorously prove that algorithm is correct or algorithm is fast or takes small space and so on. Like this one is more like intuition. This one is more kind of mechanical. Okay. And the hope is that you can rigorously convince other people about some algorithm that you came up with. Okay. You need to able to come up with it and convince other people that they are good. Okay. And the topics that we will go through in this class, I will go through this quickly, but the first part of the class is going to be about classical algorithmic paradigm. You learn again about like if you have taken 376, you learn more advanced things that is about divide and conquer, dynamic programming, and you learn about amortized analysis, like the amortization, the thing called amortized update time that I mentioned before. Okay, you learn about this. And next part is going to be about how to use randomization to speed up or make your algorithm way better than deterministic algorithm. Okay, so nowadays, like when the computational problem that you encounter is usually just so big, like the input is just so huge. It's just impossible to do things in linear time. Even linear is too big. You want to do it in sublinear time or sublinear space. How can you do this? You can use randomization. Okay. That's the next part. And the next part is linear programming. You might have heard of this thing called linear programming, but the hope from this part is that you will learn this thing as a way of thinking. You use this to capture problem that you see and kind of express it into linear programming. So that's like modeling part. You can use linear programming as a tool for designing algorithm too. So that's designing algorithm. Like use the linear programming to capture problem and also to design algorithm. You see that it's so expressive. Okay? And we will use this, like this part will be useful for the next part as well, which is how to design algorithm with like when your input is uncertain. For example, when you don't know the future, how to make a good decision for the future. Okay. So that's the last part of the course, and this is also related to ML. Okay. I will assume some basic background in this course, like asymptotic notation. We will review this thing in a discussion session tomorrow by Ben Yu. And some basic proof technique like proof by contradiction, proof by induction that I assume, like some basic terminology in graph theory, like what is graph, directed graph, undirected, path, cycle, connectivity. Okay, so like when I mention some term in class and you don't know what it is, just feel free to ask me. All right, I will just explain it, but maybe quickly. And if you don't know it, then you can look up. Okay. I will also assume that you have seen basic data structure like list, queue, stacks, heap, binary search trees, some basic algebra, and some basic probability. So we will put like some exercise on probability in the first homework so that you can brush up on this thing if you don't know about it. Okay. All right. So this is what we learn in this class. Okay. But just for fun, to illustrate this, what it means to learn new algorithmic techniques or to prove algorithm guarantees, I want to draw like an analogy between math and cooking because maybe it makes you understand this a bit more. What I mean by learning these two things. So math is like cooking. One aspect that is similar is this. So when you read a cookbook and when you read a math book, like no one actually really read it for fun, right? Like when you read it, when you the joy actually comes from experience. You don't just read it like and it's like so enticing you want to read it more. But like for cookbook, you read it so that you can taste the food. Like you can try to cook something and you taste the food. And when you read math book, you just don't read the symbol itself. You try to understand it, and the feeling of understanding that concept is like cooking. It's like tasting the food. That's when the joy comes, right? Not just like to read the symbol itself. So the first goal of this class, when I say that I want you to learn techniques or paradigm from some inferential algorithms, it's similar to like I want you to learn like some new taste, to feel the taste of the food is basically similar to understand new math concept. Right? To understand is like to feel the statement that like what it means to understand something. I mean like to feel that some statement is just it makes total sense to you. That's what it means to understand. Like it intuitively making sense to you. Okay. So the first goal is to learn like some new taste that you maybe don't even know it exists, and just to learn what it feel like. Okay, so that like maybe sometimes in the future people kind of describe what they want is something like that. Now you can come up when you remember. Okay, this is the kind of taste that you want to cook. Okay. But however, like what's different from between math and cooking is that it's something that you can only taste what you cook yourself. Okay. So when you cook, okay, you can just cook something and give the food to other people directly, but you cannot just transfer the feeling of this understanding to another person directly. That doesn't work. So in this class, what I can do is that like I'm gonna explain the argument in front of the class. That is like I kind of cook in front of you, but I cannot really give you the food itself. I cannot transfer my understanding to you. So what you need to do in class is kind of see how I cook and cook along with me, right? Follow the argument, think about it, and try to make sense on the fly. Okay, this is what you do. So try to make this concept intuitive to yourself, and ask questions if it doesn't make sense to you. Sometimes the time is short. You might just take note from the recipe, but maybe try to make sense of it at home. So taste it at home. So this is important because like without understanding or tasting the food, this class is not going to be fun at all. Like so, okay. So the second goal that I want is that you can write your own recipe. So this is what we're going to train you through homework and project and exam. That is, you're going to write some rigorous proof, similar to write some recipe that you have in your mind. This is like to train you to be able to communicate your understanding of the math concept. Okay, and like what I mean by rigorous, it means that like each step should be logical so that people can follow. The bad example is like okay. If I say like the first step is to slice some lemons, and then the second step is to make orange juice, then like it doesn't make sense. Like people cannot follow this, right? So it's very important to be rigorous. It's not the goal itself. The goal is to communicate idea, but without rigor, then one cannot verify or follow the step, right? So you need to do it. And if there is an error or your proof is not rigorous, then we will kind of deduct your point and you learn how to do it good. Okay, so that's the goal, to train you to like kind of rigorously prove some algorithm guarantee, or to train to write the recipe on top of your head. Okay. So that's the goal. Okay. And this is what it means in cooking term. Okay. So when you learn these kind of things a lot, like this can be like a kind of a good starting point to be a chef or algorithm designer. That is like once you master in recreating a lot of recipe of well-known dish, then like you might be able to create your own or invent a new taste yourself. Okay. Now how to do this effectively. Okay, so I can ask like what is a good way to cook? Like if suppose that you get a recipe and you want to learn how to do this by heart quickly, okay? Well, if you are a total beginner, it might be good to just follow every step closely and follow everything. But okay, you get each step. This might be important in the beginning when you try to understand something, but you won't remember every single step because there are just too many things. But it's good for foundation. So once you know, like at least know the foundation or every single step, then if you want to master doing something, then the best way might be just to try to cook something that like try the way that makes sense to you, and then just check the recipe when needed, like whether it makes sense or you cook something that's still like a taste what it's supposed to be, right? And repeat this. Like when you try it for the first time, it might be like something else totally, and you just need to adjust. So like try to repeat this and refine your intuition. With this, you will be able to kind of identify the key step, and even like identify what step is not needed in the recipe or in the argument. Okay. So the point is like to kind of start with kind of precision, but progress to intuition. So what do I mean by like in general how to do like this part? I think it's like this. I'm not sure if you have learned about like if you have heard about System 1 and System 2 from the work of Daniel Kahneman, but I want to mention this. So Daniel Kahneman says that every people have two ways of thinking. There are intuitive thinking. Like it's like when you understand something or you know the taste of something, it's really fast. Like imagine that I ask you like what is 2 plus 2, then you can instantly answer that because it's kind of in your mind. You know it instantly. Or you think of neural nets, like when it answers you something. Okay. So what we want is like this kind of intuitive thinking. When some people ask you, you have a feeling and you can answer that like easily, right? But there is another way of thinking. It's called System 2 or logical thinking. This is when you do when you try to verify some argument in the proof or you follow the recipe. You do this carefully, step by step, right? Or how it works is like you think of how traditional computer program works. This is a slower way of thinking, and it might take like minutes or hours to do. But note that this is the only way you can communicate ideas. When you communicate ideas, you can only communicate through like through conversation or like through some way of writing. So you want this, but you can only communicate through this. You want to improve this, but you can learn only through this. Okay, so what do we do? Like, the way to improve system 1 is basically through interaction of 1 and 2. Like, you guess, use system 1 to guess, and verify using system 2. And this kind of interaction between the two things is how you refine your intuition. And you can think of how this works like when you, it's like at the training phase of neural nets. It's like it takes a lot of effort and it's very slow, but like it might take hours or years. But this is like what we do to improve our system 1. And basically, this is what mathematicians do their whole life. Just keep trying to, like, what they don't, any mathematician doesn't want to be like a computer. They want to get a good intuition about the object that they care about. Okay? And they use this way of things to improve their thinking. Okay? If you want to learn more about this, look at this book. So this is what I mean, like how to learn effectively in this class. Okay, in the beginning, you might want to follow every single step in the argument, right? But if you really want to get good intuition about like a concept in this class, maybe one way is to like keep refining your stupid question. And stupid question is really welcome in this class, by the way. Like keep asking obvious question. Why don't we just do this? Why don't we just do that? Try the obvious approach. And once you ask this, then you can use system 2 to kind of verify whether they are like making sense or they give you something that is good enough already. And this interaction between system 1 and 2 will refine your stupid question until you get a correct answer. Another way of this to make this interaction is just, let's say you want to understand something, some statement in class. Maybe you try to sketch a proof on your own. Okay, so you use system 1 to like kind of use your intuition to guess what should be the final statement or how to prove it, and use system 2 to check each step in your argument whether it works or not. Okay, so once you see that you need to adjust your argument somehow, you keep doing this until it works. Okay, so that's how I suggest we do things in this class. And now let me switch a bit to some logistic. Okay, any question up to this point?